A pendulum can be considered a simple harmonic oscillator. Typically, we describe this motion as simple harmonic motion, or SHM, simple harmonic motion. Now let's first start by looking at a few characteristics of the pendulum's motion. So here I have a simulation. I'm going to start. And notice this pendulum is swinging back and forth. And as it's swinging back and forth, the motion is being graphed by this little dot that you see moving that represents the position of the pendulum. And then we have time on this horizontal axis. Now I've increased the amplitude to 20 degrees. And now let's start the simulation again. And notice that it's swinging out further. It's plotting the position and time. I can also choose to look at the velocity of the bob. And notice there's an arrow here showing the direction of the motion of the bob at any moment. The direction of the velocity is tangent to the path being an arc as the pendulum swings back and forth. I can also look at the direction of the acceleration. Now notice the acceleration is always pointing tangent to the path. And notice that no matter what, the acceleration is always pointing towards this position here or towards the equilibrium. And notice that as the acceleration gets smaller, it approaches zero, and it changes direction, causing the pendulum to slow down, stop, turn around, come back, slow down, stop, turn around, come back. And it does that over and over. So if our pendulum bob is out at its maximum position and the acceleration is pointing back towards the equilibrium, the acceleration points along the direction of the net force. So let's look at what our forces would be on this pendulum. So the earth is pulling down on the pendulum bob, and there is a tension force up and to the left along the cord. Now, if the angle is measured to the horizontal here, then I would need to also measure the angle to the horizontal there. Now, if the net force is in the direction of the acceleration, that means that my net force is going to be along this line. So let's add an axis along that direction. Now I do that because it is always easier to put the net force in one dimension. And so if the net force is along the direction of our net acceleration, just like we saw in the simulation there, then I will want my axis to be in this direction. So that means I need to do a little geometry to figure out where this angle belongs. If my blue dotted line is an extension of the direction of the tension, then this angle here would also be theta. If we let the green axis be the x-axis and the blue axis be the y-axis, then my net force along the x direction, which is also the direction of my net acceleration, which is the same direction as my net force, then we can write the sum of the forces in the x direction is equal to ma sub x, because that's the x direction, and the force that is in that x direction would be the component of the weight pointing along that direction, And so it would be opposite of the angle, so that's a sine component. So FG sine theta equals MAX. Now that's not X is in position, but that is X is in direction there. So that means that mg times sine theta will equal m times a. Now let's consider the position versus time graph. So as this pendulum bob is moving in its arc path, we can imagine that the shadow of that bob is going back and forth on the floor here or below it. And so even though it's traveling in this arc path, let's think about looking at the shadow as it comes back and forth here. And so if we graph that, we start out at a positive position, and it's going to go up and down, back and forth. Now from your math class, you probably learned that that is a positive cosine graph, and that we would have the cosine of some radian angle. Now the coefficient in front of the cosine would be A, as in the amplitude, so how far it goes, and then this would be our angle. Now, in order to not confuse the angle of the position of the string with the angle of the motion, which would be related to the cyclic motion. So remember, even as this object is moving in this arc path, it's completing a cycle. And so there are 2 pi radians in that one complete cycle there. We can describe the cyclic motion, the speed of that cyclic motion, as being the angular speed. That is a lowercase omega. It's a Greek letter. But the angular speed tells us how many radians per second this cyclic object or system is moving. And so I can find the angle in radians if I have the angular speed and I multiply it by the time, because radians per second times seconds would give us radians. And so inside this parentheses, I'm going to write omega t. So the position function would be a cosine of omega t, where omega is our angular frequency or angular speed, how often this system completes a cycle. We can then evaluate the velocity of our particle that is in this simple harmonic motion by taking the derivative of our position function. Now, if I have velocity on the vertical axis and time on the horizontal axis, now this velocity is that tangential velocity that we looked at in the simulation. So initially, the velocity should be 0 because we're starting out with the pendulum pulled all the way up. Since the pendulum is going to move in a direction that is down and to the left here, and our tangential velocity will be directed along the same line as the acceleration, I'm going to make that the negative direction, and then as I come back, I'll make that the positive direction. So swinging left and then swinging right. So then it speeds up, moving to the left. It slows back down when it gets back up to the highest point on the other side. Then it speeds back up as it returns to its original position. And then it slows down as it reaches that start position. And so we're beginning to see what looks like a negative sine curve. And if I remember, the velocity is the derivative of our position function. So the velocity would be the derivative of that a cosine omega t. And so the derivative of the cosine of omega t, a cosine omega t, would be a times the negative sine of omega t times the derivative of the argument here, which would just be omega. And so then we have that the velocity with respect to time should be equal to negative a omega times the sine of omega t. Again, this omega is our angular frequency, how often it comes back, or the angular speed. So we can call it angular frequency. Either works. So now I have an expression for my velocity. Now, why did I do this? Well, I am looking at this free body diagram that we've drawn way up here, and this acceleration is when the object is at the highest point or its maximum position. So I want to figure out, what is that acceleration? So let's consider this acceleration. Now, initially, the acceleration is very big. It's at a maximum because the pendulum is pulled the furthest back possible, but it's pointing in that left and down direction that I decided would be negative. So I'm going to have a negative acceleration, and then it's going to become 0 as it passes through the equilibrium position. It'll become positive, it'll become 0, it'll become negative, and we begin to see a negative cosine curve. Now you should also remember that acceleration is the derivative of the velocity with respect to time. So if we take the derivative of this velocity function up here, then we would have negative a omega times the cosine of omega t times the derivative of the argument there. And so I would have a is equal to negative amplitude a omega squared, because I'm going to bring that guy over, times the cosine of omega t. And so this negative sign is in line with this negative sign here, and it all matches up. So I've done this so we can evaluate, what would the maximum acceleration be? Well, the maximum acceleration would occur when the cosine of omega t is the largest it can ever be, which is 1. The cosine of any angle, the maximum is 1. And so if the cosine of omega t is 1, then our maximum acceleration would be negative a omega squared. Now, because acceleration is a vector, this negative sign right here is very particular to a certain spot. So the magnitude of the maximum acceleration, we could just take the absolute value of that. So now let's take this and substitute it back up there. So that would give us that mg sine theta is equal to m times capital A omega squared. Now remember, capital A is the amplitude. That's the maximum amplitude of our original position function. So I can do a little algebra here and divide by m on both sides. And so then I have an equation that looks like g sine theta is equal to a omega squared. The amplitude in this case is the arc length, which would be the length of the string, times the angle we pull it back. I can use what's called the small angle approximation, and that is for very small values of theta. The sine of theta is approximately equal to theta. So if you were to take your calculator, make sure you put it in radian mode, and take the sine of a very small number, like 0.1, you'll get approximately 0.1. So then that means I would have approximately g theta equals L theta times omega squared. Now, again, notice we can do a little bit of algebra here and we can divide by theta on both sides. And so then we get an expression for omega as being the square root of g over L. Now, from our discussion of the pendulum lab, we found that the period was equal to 2 pi root L over G. Now notice this is the reciprocal. So that means that I could write period as being 2 pi over omega, because the reciprocal of omega would be the root L over G. So then period is the time per cycle, and if period is the time per cycle, frequency is the number of cycles per time. So frequency is one cycle per period. So frequency is the reciprocal of the period. So that means that we could write this as being equal to 1 over the frequency, or we can say that frequency is omega over 2 pi. These are just different ways to describe the motion of our pendulum. So now that we have an expression for omega, then we can write the expression for the motion of our pendulum. So when you say that the position is A times cosine of omega t, this omega, this angular frequency, is equal to the square root g divided by the length.